All right, so we already talked about how the whole diffraction pattern of light as a wave exists from a double slit via Young's famous double slit experiment. Well, it turns out that this phenomena also takes place with a single opening or even a barrier, which is a little weird because if you think about it, that means if I'm shining monochromatic light on an opening, somehow it turns into a diffracted wave and creates an interference pattern, which does imply that the light wave itself is interfering with itself, which is strange to think about. But if you remember Huygens' principle, it's that idea that light itself is actually a bunch of individual wavelets that are propagating forward to be treated as one overall wave. If you remember that, then you can almost perhaps see how these individual wavelets will take their own path. And so when we're getting self-interference, it's really these wavelets interfering with each other. Now there's a whole lot of geometry that comes into play here to try to prove the equation, and I'm going to bypass a lot of that math proof for you because I don't know how necessary it is, but if you're interested, and I encourage you to look it up. But two things that we got to understand in terms of single slit diffraction: you're going to get a central maxima. This central maxima will be significantly wider than what you get with a double slit interference pattern. It'll be significantly more intense. It'll be by far the brightest dot. The remaining maxima do occur, but they're significantly lower in intensity. So these peaks that I'm showing is an intensity graph. You can sort of see a diffraction pattern right now on this simulation here to the right. You can see how it's going to be brighter right here. But you can also see where that brightness kind of repeats itself again further outward. Let's break it down a little bit in terms of the geometry. I'm just not going to break it down a lot of it. So typically the wave will enter the opening. Now d in this case won't be the distance between two openings because we don't have two openings. So this d we often write as capital D to show it's the distance of the opening itself. So it's the barrier or the opening width. Now you can go ahead and look at this slower on your own, but ultimately what this implies is that there are really four distinct zones that we have to look at for this opening, where the two top fourths are interfering with each other, and then the third and fourth are interfering with each other, but then also with like the first and third fourth are interfering with each other, and the second and fourth quarter are interfering with each other to get these odd patterns that end up basically what it ends up showing. Again, if you follow the geometry, which I'm not going to go through in excruciating detail, it ends up showing that for a dark spot, not a bright spot, a dark spot, which is destruction, we're going to get this equation here: d sine theta equals m lambda, with d being the distance width of the opening itself, theta still being the angle between where that bright spot exists on the screen and the center line, so we would draw a center line. M is still increments of whole numbers, 1, 2, and 3. We will not have m equaling 0 here, so the smallest value is m equaling 1, and lambda is still the wavelength. So this looks like the double slit equation for constructive interference, but it's not. Remember, it's the single opening for destructive interference. Now there are ways we can predict where the bright spots are, but it's actually not as straightforward as a simple equation takes place. It's not going to be in any incremental fashion that we're going to lay down for you because of this awkward interference of self-interference. So we really can only predict where the dark spots exist for single openings. We're not really going to be able to figure out directly where the bright spots exist, although you can assume correctly that the bright spots do exist in between the dark spots, just not exactly in between the dark spots. This phenomenon takes place with a barrier or a disk as well. So if we have, and this is really weird, and this is actually where back in the day a lot of scientists completely dismissed this idea. They said, no, that's not true at all. And I believe it was Fresnel. He said that if we take light and shine it on a solid disk, we won't have a complete shadow like everyone sees in real life. What we'll have is this bright spot in the dead center. Now this is weird. This idea that light will basically bend around the disk and then interfere with itself in the dead center. And it turns out, and this wasn't proven for many years later, that this was true. That, yeah, we do get a diffraction pattern. Here's a very profound one. You see almost like bullseye rings. And here are your maxima. So you see your minima are the dark bands, and your maxima are the bright spots. You can see this phenomenon with a sphere as well. If we shine monochromatic light on it, you will get a shadow like you would expect, but then you will get interference. And you get a nice bright central maxima, and then some other maxima leading off of it. And they do dissipate pretty quickly. The intensity of light goes down quite a bit, so you won't be able to see too many of these spots, but it does exist. So again, remember that d sine theta equaling m lambda only is true for the dark spots, the minima. So what happens when we go from one or two openings to many, many, many openings? Well, we get some pretty awesome stuff. In fact, in class, we're going to do a few labs on this. It's pretty neat. And it's the concept called the diffraction grating. So what happens when we take thousands of openings? Tens of thousands for some of them. In fact, most have 10,000 openings in a just simple centimeter of glass. So picture a centimeter-sized space, which is not big at all, and somehow create 10,000 openings there. It's very, very difficult to see. You can't even feel it if you had one of these diffraction gratings, but it's true. Ends up having a very, many, 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 many different spots where we get construction and destruction. And geometrically speaking, it ends up creating a very similar equation as our double slit interference equation. So I'm going to drop the equation down on you right now, and I'll try to kind of explain it again in a second. But we have d sine theta equals m lambda, which is the exact same equation as we have for the double slit. The one big difference is d. For the double slit equation, d was the distance between two openings. For diffraction grating, d is not that. It's the distance of each opening, which is really, really, really tiny. So if I have 10,000 lines per centimeter, then one of these lines is 1/10,000th of a centimeter. And that's just of a centimeter. So if you convert it to a meter, it's going to be an even tinier number. Very, very small value. This equation is indeed true for your maxima. So d sine theta equals m lambda, with m being 0, 1, 2, and 3. And we're not really going to use this for minima. We're going to specifically use this for maxima. So if I were to look at, an exaggeration here, remember there are really 10,000 of these openings, not just 5. But if I were to shine white light on this, that white light will actually start to separate into the rainbow. And we get a spectral order. And so in the very center, we're going to get a white band. Then we're going to start to see a rainbow. So this white band is our central maximum. This is where m equals 0. Then we're going to start to get the rainbow pattern. We're going to get at m equals 1. We're going to see that violet will start to separate more than the red. And that's because violet's wavelength is shorter than red's. So if its wavelength is less, its angle is less. So it's going to land on the screen closer to the center line. If I were to draw a line here, that would be the theta for violet. And then for red, that line it's more exaggerated in this particular picture, but that angle is definitely bigger, and it's because red's wavelength is larger. And so you'll get your m equals 1 on equal sides of the central. And then you're going to get your second order even further out, m equals 2. And you're going to get that rainbow to repeat itself again. It's actually a pretty neat looking thing to see in real life. If you aren't present for the lab, you can easily get diffraction gratings on Amazon, pretty easy. Just type in diffraction grating, or even type in spectral glasses. They're pretty cool little glasses that you wear. It separates the white light into the rainbow. As you'd probably expect, that first order will be brighter than the second order, and then intensity will taper off as you get further and further away from the source, because that light is traveling further and further. Right, here it is in a three-dimensional view. White light strikes that grating, and then bam. Now, if we limited it to a monochromatic source, instead of this white light being red light, then just all of this part just wouldn't exist. So you'd have this would be red in the center, and then red again here, and then red again further out, and you'll just get red patterns everywhere. The reason why it's white in the dead center when we're shining white light is because we're not getting any separation. Theta is 0 for every wavelength, so you're getting RGB on top of itself, which is white light. It turns out that CDs actually use this principle of diffraction gratings. This is one way in which the CD is able to transmit information. It's a pretty impressive technology. CD has really tiny grooves in here and little bumps in those grooves, and we shine light inside the CD player, shines a red laser down on those grooves, and it basically measures the pattern that comes back from the reflection, but that pattern exists due to the diffraction inside the grooves. Now it's a little bit more complex than I'm alluding to, but if you look at this equation, d sine theta equaling m lambda, if I'm using red light as my wavelength, then I'm limited to how small my opening can be. For example, if I want to set theta and m as some set value, I can see how lambda and d are related to each other. Now, Blu-ray DVD uses a blue laser. Well, the blue laser is smaller wavelength. Since the wavelength is smaller, my distance between my opening can be smaller, which means I can have more grooves in the same space. That's why a Blu-ray DVD, which looks like the same size as a CD or a DVD, can actually pack in more information because the grooves are tinier and they're closer to each other. Here is an example of shining white light through a diffraction grating and seeing the pretty nifty rainbow effect that takes place. And here is the same concept, but instead of using white light, we're using green. So you'll see the center maximum is the green, and then the first order is the green again later, and you'd probably see it again later on. And we're not seeing all the other colors of the rainbow before and after it because simply they didn't exist. It was just green light. Now, the concept of diffraction grating, separating the light source into the individual maxima and minima, is how we are actually going to use this in the world of spectroscopy, which is a pretty large world. It's not, just limited to one source, but it's this concept that we will take and measure the wavelengths of light from a gas to determine what the gas is made up of. Now, if you've taken chemistry, you will remember or understand that the electrons in a gas will get excited and then they will return back to their ground state. And when they do that, they'll emit a photon. Now in physics, we're going to learn about this in future chapters, but recognize that every gas, when excited, will end up emitting a characteristic of light. And if we look at, say, hydrogen gas while it is excited, so if we had a hydrogen lamp, which is basically just a lamp with hydrogen gas in it, and we hook it up to an electric potential, it's going to create a signature color light. Now, if we look at that light with a diffraction grating, we will then be able to separate the individual Roy G. Biv, the individual frequencies or wavelengths of light, to understand what that blend of light is actually made up of. So let's rewind. If I was looking at white light, and I shined it through a diffraction grating, I would get this even blend of the rainbow, but every single color is being represented here. If I'm looking at white light and I were to make a spectral graph, I'd see all of the colors blended together. Now, if I take hydrogen specifically, hydrogen will not shine every frequency of light. Instead, well, it looks like there's only 4 of them here. So if I were to look at a hydrogen lamp with diffraction grating, I will see individual purple, this bluish color, this greenish color, and this reddish color. But there's a specific wavelength to each of these that we can calculate and measure. Same thing's true for every gas. So if we had a mercury lamp or a neon lamp, we'd start to see these individual patterns. Well, if you were a scientist and you were curious as to what the makeup was of a particular gas, if you shine it through a spectrometer, you can find this quote-unquote fingerprint, and you can lay it down on a chart and compare it to every other known gas's fingerprint, and you can figure out what it's made up of. This is exactly how, in some extent, how forensic scientists are able to determine the chemical makeup of materials. They will basically burn it, and then as they burn it, they will look at the flame that comes out of it through a spectrometer, and they will be able to determine the various different makeups of the particular particles or gases that are inside of it. So if I were to combine hydrogen, mercury, and neon into the same lamp, and I were to excite it, we'd see a blend of all of this, but we would then be able to separate each individual band to determine the relative makeup of that particular material. This is also how astronomers are able to look at distant galaxies, or maybe not galaxies, distant solar systems, and have a pretty strong idea of what the gas makeup is of the atmosphere of planets that are orbiting said stars. And they basically just look at that light that's coming to Earth, and they run it through a spectrometer, and they're able to figure out the bands. Now that's a little bit more complex than I'm making it sound, but the basic principle is here: spectrometry or spectroscopy. All right, let's do a quick recap before I end this. This is going to be it on the whole concept of wave interference. We have three very similar equations but are not the same. You've got the double slit equation, which is d sine theta equaling, and for constructive interference, you're going to get m lambda. So this is construction. And for destructive interference, you'll get d sine theta is equal to m plus 1/2 lambda. Recognize that d is the distance between the openings. For the single slit, you're going to get capital D sine theta equals m lambda. But this is only for destruction. We will not use this for construction. And recognize that d is the size of the opening, or the barrier, not the distance between two. And then you've got your diffraction grating equation, which looks like the very first one, d sine theta equals m lambda. Again, this is for constructive interference. But understand that d is the size of one single opening, and there are usually thousands and thousands, so this value is usually really, really tiny. You can approximate where the minima are as well using the m plus 1/2 rule that we did for double slit. This is not as common, but it does work. Okay, that's it. Thank you.